Start back up. Okay. So here we've talked about discussing the form and the direction and the strength of a relationship. Okay. So yeah, let's just try. So tell me what you think would be the direction and the strength of a relationship. Don't shout out the answer. Just think for a moment. Okay. All right. Maybe the number of bedrooms in a house and the number of square feet in the house. Okay, so don't shout out your answer. We have positive, negative, strong, weak. All right, so number of bedrooms and the number of square feet, what do you think you got?
Positive, weak relationship?
I'd say positive, pretty strong, fairly strong. Okay, it's not going to be perfect. Okay, but generally, if you got a house with more bedrooms, there's going to be more square feet. Okay, because if you got a small house, you just can't add more bedrooms to it. Okay. All right. Well, what about maybe number of bedrooms and the value of the car in the garage?
No relationship.
Number of bedrooms and the value of the car in the garage at that house.
Probably.
Yeah, I'd say a positive relationship, and then yeah, on the weaker side. Okay, but generally, larger houses will have cars with higher value. Okay, in general. Okay, or do people disagree with me there?
I do.
You do? That's okay. That's okay. All right, but I would say in general, families with larger houses, in general, tend to have more money, tend to have more expensive cars. Okay? These are overall trends, not. Yeah, sure, you could find any one particular house that's huge and has a terrible car, or you could find a terrible house but with an expensive car, because people have different tastes. All sorts of things like that. But in general, there is an overall trend that appears that way. Okay? Yeah, you know, all sorts of things. Okay? There's a positive relationship, believe it or not, between the number of kitchen appliances and the reading ability of a student. Okay? I'm serious. Look at the data. Okay? Census data, number of kitchen appliances, reading level of a student. Okay? It's all kind of tied to income. But in general, households with lots of kitchen appliances, okay, in general, tend to have more money. In general, families that tend to have more money, their students tend to have a higher reading level. Okay? Whether that's fair or not, that's just the reality of the data. Okay? It's a weaker relationship. It's not incredibly strong, but it exists. It exists. Okay? Okay, so and that emphasizes another point, okay? Just because a relationship exists doesn't mean there's a cause and effect relationship there, okay? So if you look at the data, yes, you will see a relationship between the number of kitchen appliances a household has and the reading level of their children, okay? You will see a relationship. Does that mean the problem or the solution to solving childhood illiteracy or just reading problems and stuff is to give everybody kitchen appliances? No, that's not going to solve anything, okay? That'll just give people kitchen appliances, okay? It's not going to help students read better, okay? Yeah. The reasons, the why, is much more complicated, okay? It's much more complicated. Even the answer of giving people money, okay? Because things seem to be linked to income and money and things like that, okay? Even income in of itself is not the answer, right? They seem to be linked to these things, But even that doesn't explain why. Why do families that tend to have more money, why do they tend to have children that have higher reading levels? Why? Okay, the money isn't the answer. It's just there's all sorts of, the answers are complicated. Okay, so statistics can't give you the answers to all of these things, but it can point out trends and relationships like that. Okay, so don't jump to cause and effect conclusions. Okay. All right. So all of this stuff. So what are the three things we can talk about when we're talking about a relationship between two numeric variables?
Positive, negative.
Okay, so that's the direction is one. What else we got?
The form.
The form
The strength.
and the strength. Okay. All right. So maybe I didn't want to do that. How can we tell if something has a linear or nonlinear form?
By the graph.
By graphing it. Okay, that's really the only way we can tell if there's a linear or a nonlinear relationship. Okay, we have to create a scatter plot. We must graph the data. Okay, make a scatter plot. Okay. And at this point, because this is introductory statistics, we're not going to learn anything more beyond making a scatter plot to decide if it's linear or nonlinear. Okay, you're going to make a scatter plot, and you're just going to eyeball it and say, that looks linear, that doesn't look linear. Okay, that's all we got. All right. If you want to pursue statistics at a higher level, sure, you can learn more complicated tools to decide whether something's linear or not. But here, this is what we got. Okay. Once we decide it's linear, okay, we can just look at the strength and direction. Okay. Okay. We can just describe the direction and strength. And we have a number that summarizes the direction and strength. Okay? And that number is called correlation. Alright? The symbol for correlation is R. And it's just a number that summarizes direction and strength. Just like the standard deviation summarizes what? Spread. Okay? It summarizes the spread of the data. So does the IQR. Okay? What does the mean summarize?
The average.
Yeah, the mean. The mean summarizes the center. Okay, the middle-ish. Okay, the median does also. All right. So we have numbers. Okay, we have the mean and the median that summarizes kind of where the middle is or the center. We have the standard deviation, the IQR, and the range to summarize the spread. And here we've got correlation to summarize direction and strength. Okay. can be in between negative 1 and 1, okay? So if this is too complicated for you, if you don't like symbols, okay? R can be any value between -1 and 1, inclusive. If R is positive, the sign of R is the direction of the relationship. Okay, so if R is positive, you got a positive relationship. If R is negative, you got a negative relationship. Sign of R is the direction. And if R is close to 0, or if R equals 0, you have no relationship. Okay? If R is close to 0, so what are numbers that are close to 0? 0.1, negative 0.1. 0.2, things like that, okay? If R is close to 0, the relationship is weak. So things like R equals negative 0.15 or R equals 0.1, things like that. Those are weak values of R. Alright? If R is far from 0, the relationship is strong. Okay, so that's like R equals 0.9 or R equals negative 0.85, right? Those are strong values of R. Yes?
What about like the things that fall in between?
In between. Then the answer is it's in between, right?
Okay.
It's in
so you
between weak
have-
and strong, right? So you can have a weak person, you can have a strong person, and you can have someone in between, right? Same thing with relationships. Strong relationships, weak relationships, things that are in
Maybe like
between.
an average.
I don't know about because average has
Yeah.
such strong meanings in statistics. I would avoid that, but
Normal.
I would just say things in between, okay? Moderate, okay? And these are all kind of it depends on the context. It depends on the context. All right. So if you're dealing with robots, you would expect R to be close to 1, 0.99, 0.98. Okay, you're dealing with mechanical things. Okay, you expect R to be 0.99, 0.98, things like that. If R hits 0.8, you might be like, oh my gosh, something is terrible with this machine. Okay. On the other hand, when you're dealing with people, you will never see R equal to 0.9. Okay, because people are unpredictable. All right. When you're dealing with people, the best you might see will be R equals 0.7. Okay, and when you see R equals 0.7, you'll be like, wow, this is a breakthrough relationship. We've never seen something this strong before. Okay, whereas most of the time you're expecting things like R equals 0.3 or something like that. Okay, so it depends on the context and situation. So with robots and machines, you're expecting very high values of R. With people and other things that are much less predictable, you know, R equal to 0.7 might be considered strong. Okay, but these are just kind of general ideas. Far from 0, R is strong. Okay, the relationship's strong. Yes.
At the corner it says R equals 0.9 and then it says R equals, is that minus?
Yeah,
0.8?
negative 0.85.
Okay.
Yeah, because that's far from 0, right? If R can be anything between negative 1 and 1, on the negative side, the most it can be is negative 1. So R equals negative 0.85. That's pretty strong. Okay? Well, of course, depending on the situation, but that's a rule of thumb. Okay, so what might be R in this picture view? Yeah,
Zero.
R is going to be 0 or pretty darn close to 0, okay? Because when you throw things into the computer and it calculates R for you, it might say there's some ever so slight, okay? Yeah, down here we also have R equals 0, okay? What about over here? Yeah, you know what, actually, something like this, 0.1 is really, really scattered, okay? So this is probably closer to R equals 0.35, okay? And what about this one?
Minus 0.35?
Yeah, R might be minus 0.35, okay? Okay. Over here?
R equals 0.7.
Yeah, this is probably going to be R equals 0.98 or something, okay? Over here? Minus 0.98, okay? Something around there. Something around there. Is that okay? Alright. R is only meaningful when you have a linear relationship, okay? If you have a linear relationship, R having these values is meaningful, okay? But be careful, you can calculate R even if you don't have a linear relationship, okay? But in that case, you've calculated a meaningless number, okay? You've got a number, but it's not useful to you. So, so how do we make sure that we have a linear relationship? What's that? You must graph the data and make a scatter plot, okay? Okay, so just a warning. Okay, R, or the correlation, can be calculated for nonlinear relationships. Okay, but they are only meaningful So if somebody says we have data and the R equals 0.7, what should you say?
Is it a linear relationship?
You should say, is it a linear relationship? Can we graph it just to make sure that we've got a linear relationship before we start doing all this other stuff with R equals 0.7, okay? Because if you have, let's say you have data that looks like this. Is this a linear relationship? No. But if we calculate R, it's just going to try to fit a straight line to this, and it'll do something like this, okay? And then it basically tries to figure out how much scatter there is, and it might give you R equals, 0.65 or something. Okay? This number is meaningless because what you really have is a nonlinear relationship. It appears this way, okay? We actually don't know what happens over here, okay? But it appears that's our data, okay? So this doesn't work, okay? This is not a linear relationship. Okay. Correlation would be not appropriate. this okay? All right. So sometimes we want to figure out, let's say we go through we gather some data and we graph it and it looks linear, we calculate correlation, okay? So let me just make a side note. All right, calculating correlation, it's a complicated and tedious process. All right, you can do it, but we don't want to. Okay, we're gonna just, and today statisticians would never calculate correlation by hand. Okay, they could. If you said, Mr. Chen, calculate correlation by hand, and I'll pay you $1,000, I'll probably do it. Okay, but I wouldn't want to. All right, we just ask the computer or a calculator to calculate correlation for us. Okay, so calculating correlation, or R, is tedious and complicated. Okay, so in this class, whenever we have a data set, I will just give you R. Okay, I will say we gave this to a computer, and the computer calculated correlation. Okay. Okay, so we use computers to find R. Oops, lowercase r. R for S. Okay, and I will provide you so anytime, okay, so I will give you R, alright? But again, it's your responsibility to decide whether using R is appropriate or not, okay? Because I could also show you a scatter plot, and you have to decide, oh, well, does that make sense? Is that okay? Alright, so the book talks about calculating R. It also kind of glosses over it. It throws up a formula and says this is how we calculate R, but it doesn't really get into the details. It just says, okay, so we calculated R, and here we go. All right, anyway, once you find correlation in all of this data set, we can look for the line of best fit. Line of best fit, or this is also known as modeling a relationship. Okay. What is a model? Okay, not a fashion model. But what is a model? Even like a toy model.
It's like a sample.
It's a simplified representation of something in reality. Okay? That's a working definition? Works well enough? Okay. So a model So we could create a model for the height of students based on their age in elementary school. Okay? And that model might be every year a student grows 1 inch. And at age 10 they are this tall or something. Okay? Now, is that the reality? No. Every year all students do not grow exactly 1 inch. Some students grow more, some students grow less. But it's a simplified representation. Okay? Overall, it seems every year a student grows 1 inch. I don't know if that's even true. Okay? Making up numbers again. Okay? But we could say something like that. Okay? So we could say, so for An example model could be, on average, maybe 1 inch each year. And at 10 years old, the average height Who knows? I don't know. I'm just making stuff up. Okay? So don't. Maybe it's probably closer to 2 inches each year or something. Yeah, let's say that. 2 inches. Okay? And that would be a model. Okay? It's not super accurate, but it could work. Who knows? Is that okay? Alright, and we could represent this mathematically too. Okay? We can. So according to this model, what is the average height of an 11-year-old? Okay, so don't shout it out. Think of the answer. So according to this model, the average height of a 10-year-old is 54 inches. According to this model, what's the average height for an 11-year-old? Don't shout out the answer. Think of it. Okay, what's the answer? 56 inches. Does that make sense? Okay, and what would be the average height for an 8-year-old? Again, don't shout out the answer. Just think of it in your head. Okay, and your answer is?
52.
8-year-old? 50 inches, right? 8-year-old is 2 years younger than a 10-year-old. And if each year student grows 2 inches, an 8-year-old, the average height would be 50 inches. Okay? Is that okay? This is actually a mathematical model, okay? And we could represent this using an equation, okay? A linear equation. Alright? So if somebody says, okay, I'm going to, the predicted height is equal to some number plus every year the height goes up 2 inches each year, right? 2 inches times each year, the number of years. Years or age. Age in years. Is this okay? Alright, so I'm going to just tell you the answer. Alright, and we could say the predicted height is equal to 34 plus 2 inches times age in years. Okay? Alright, and we can see that this kind of works, right? So if I plug in a student who is 10 years old, a 10-year-old, we would do 34 plus 2 times 10, and what would we get? 54, right? Can we see that? 2 times 10 is what? 20. 20 plus 34 is 54. Okay. And an 11-year-old, I would do 34 plus 2 times what? 11. And when I do that, I would get 34 plus 22, and I would get 56. Yes?
Where did you get the 34 from?
Okay, I'll explain that. Okay, but I'm just kind of showing how a linear model, a model works, right? And this is called a linear equation because it forms a straight line if we were to graph this. All right, this is where we're headed. Is this okay? All right. Do you guys remember in algebra we had y equals mx plus b? Okay. Can you guys kind of see the same form here?
Right.
Okay, except we move things around, okay? Here, the age, this is my x variable. Okay, is that okay? So this was the x. The m, what is that called?
Slope.
That's called the slope, all right? And over here, this is the slope. All right, and this was the intercept. And so over here I've got the intercept. Okay, so we are plugging in the x variable, which is the age. We'll multiply it by the slope, we add the intercept, and so that would make predicted height what? This would be our y, okay? Our predicted y. Okay, so, all right, so this is an example of a linear model, and then so we'll break this down and we'll define all the little parts and pieces. Is that okay? Does this work? Okay. Can you guys see how that that's a mathematical representation of this thing? On average, a student grows 2 inches each year, and at 10 years, the average height is 54 inches. Okay. So this is kind of what we have, and then we turned it into that. So this is known as a linear model, also called a linear regression model. Or sometimes just regression model. They're all kind of used interchangeably sometimes. Multiple names for the same thing. Same thing. Okay? We write it in the form y hat equals a plus bx. So it's not y equals mx plus b. We had to change things around. And now the b is the slope, and now whatever, okay? The hat, this little cap on the y, this means this is our prediction for y. Not the actual value of y, but our prediction for y. Anytime you see a hat, it means our prediction for y or something based on our data. Okay? So our prediction of y. Y is what? Our explanatory or our response variable?
Response.
Yeah, y is the response variable. Okay. The response variable, or what's the other word? Dependent or independent? the dependent variable, okay? Okay, in our example, y is age or height?
It's height.
It's height. In our example, y is height. Okay. The a, this is our intercept. Okay. And b is our slope. And x is our, I'm drawing a blank here. Another explanatory variable, sorry. Sometimes that happens, right? X is the explanatory variable or the independent variable. Or the name in our example, it is age. So in our example, that we had, I'm going to just write it symbolically, y hat equal 34 plus 2x. Alright? Another way I could write it is I could write height, and I could put a hat over it, and this means our prediction for height is equal to 34 plus 2 age. Or the most verbose way was to write predicted height equals 34 inches plus 2 inches per year times age. Yeah, we'll just leave out with this. Okay? So we could say, what is your prediction? Prediction for y when x equals 8 years. And what's your answer? You would say y hat is equal to 34 plus 2 times, what number goes here? 8, okay. I guess there's a, let's assume that there's a times here, 2h, is that okay?
Yeah.
I know some students get confused, okay? So I'm gonna just do a little x for times, 2 times 8. So I have y hat equals 34 plus 16. Y hat equals 50 inches. So this is our prediction for y when x is 8. Okay. Is that all right? Okay. So how do we get the 34 and the 2? Okay. Well, so 34, that's our intercept. That's A. and the 2 is our slope b, okay? So, in our example, I didn't present you any data, I just presented the model first, and we came up with this equation here, okay? And I kind of just made up the equation here, okay? Sometimes, we want to figure out the A and the B that's going to give us this line, okay? So the best fit line, so if we are basing it on data, okay? So to find the best fit line for the linear regression model or whatever it might be, based on data, okay, we need to know some pieces, we need to know 5 things from our data. Okay, the first, or the last, whatever, these are kind of in no particular order. One of them is R. We need to know R, what is that?
Correlation.
The correlation between X and Y, okay? This is the correlation between X and Y. Okay? We also need to know X bar. What's X bar? The mean of X, okay? And what would Y bar be?
Mean of what?
Okay, we also need to know the mean of Y. Alright? So what is the mean of X and what's the mean of Y? Okay, well if we have data points, alright, we have different students, and we have their age, which is our X, and their height, which is Y. And we have a 10-year-old who's 54 inches, and maybe an 11-year-old who's 55 inches, and a 9-year-old who's 51, and an 8-year-old who's 50 inches, and stuff like that, okay? The mean of X would be, if I take these 4 numbers, I add them up and I divide by 4. The mean of Y is I take these 4 numbers under the Y column, I add them up and I divide by 4. Okay, so that's the mean of X and the mean of Y. Is that okay?
Yes.
And then I need to know the standard deviation of X. So I'm going to write SX to write the standard deviation of X. And then I need to know the standard deviation of Y. So that's SY. Okay? And just like you had to do on your quiz, standard deviation of X would be take these 4 numbers and find the standard deviation. Standard deviation of Y, take these 4 numbers and find the standard deviation. Okay. So once I have those 5 numbers, now I can find my best fit line. Okay, so requires a little bit of work, okay? So with the exception of R, you are able to calculate X bar, Y bar, S sub X, and SY, right? Okay. Hopefully you don't have a billion data points. And I might even be nice and provide you with some of those numbers so you don't have to calculate them all. But you have a question? Or? Okay, everything's good? Alright, so once you have these 4 numbers, first you find the slope. Find the slope. B is our slope. Okay? And B is equal to R times the standard deviation of Y divided by standard deviation of X. Here. Then, once you find the slope, find the intercept. Okay. And A is equal have that, you put them together, and you have y hat equals a plus bx, okay? Do we need to solve for x or y hat? No, we leave these as placeholders for our model, right? Because the model says, give me an x, and I'll give you a y. Okay, so all you need are the a and the b. You don't need to figure out x and y because they're placeholders in the model. The model says, you give me an x, you give me an age, and I will give you a predicted height. Okay, so we leave those as placeholders. Okay. So, so in the last example, with the height, I didn't give you the standard deviation of y and the standard deviation of x and the correlation and the mean and this and that. Okay, I didn't, but we can do that. Okay. So let's say so I'm making up data here, but I'm going to try to get it to match what we had before. Okay. Say r is equal to 0.6. Okay. And let's say maybe not at an elementary school, but at a, I don't know, let's say we have a bunch of students, and we say the average age was 10, and the average height at 10 years old was 54 inches. I gotta figure something out here. Okay, so let's say S of y was 3, and S of x is 0.9. Okay? So this is based on our data. Okay, so let's say we had all those numbers, we calculated the mean of x, the mean of y, and this is what we have. These are the 5 numbers that we need. Okay? We could figure out, based on this, figure out our model. Okay? So b is equal to r times s of y over s of x. Okay? So r is 0.6, s of y is what, 3, and s of x is 0.9. And when I do this, I should get, I hope I did this right, I get 2. I get b is equal to 2. Is that okay? So this is my slope. So I have my slope is 2. So how did I get that number for the intercept? I say a is equal to y bar minus b times x bar. Okay. So what numbers do I plug in here? I plug in 54 minus what? What is b?
2.
b is 2, and what's x bar? 10. Okay, so I get 34. Okay, so that's how I got the 34. Okay, and this is my intercept. Is that okay? Okay, so we have 2 as our slope and 34 as our intercept, and so we could write y hat is equal to 34 plus 2x, or I could write height with a hat, so predicted height is equal to 34 plus 2 times age, because age is our x variable. So far, so good. Okay, so let me talk about the interpretation of the slope and the interpretation of the intercept, and also something called residuals. All right, my slope is 2. What does the slope mean? What is the meaning of the slope? slope equals 2. So what does that mean?
On the chart, you just go like that one.
Huh? Slope is equal to 2.
It's the rate, it's the rate at which the scatter plot, is positive.
Alright, just think back. Okay, you guys are saying stuff like rise over run, which is a terrible definition for slope, okay? Because there's no concept behind this. My slope is 2. But where is this 2 coming from? What was the original model that I had in words?
2 inches.
It says what?
2 inches.
Every year,
A
a child grows 2 inches. That's where this 2 comes up, okay? It means every time the age goes up by 1, okay? Whatever your x variable is, whenever you increase that by 1, so in age it means the child got 1 year older, okay? If we were talking about something else, it means you've increased your x variable by 1. So if we were talking about, you know, the amount of ice cream you sell and the temperature outside, okay? If x is the temperature, every time the temperature goes up 1 degree, we can expect to sell this much more ice cream, okay? So here, this means every time I increase the age by 1, okay, we expect, okay, and it's important that we write we expect that height goes up by 2 inches. Okay? And that's the meaning of the slope. That's the interpretation of the slope. Every time I increase the age by 1, we expect that the height goes up by 2 inches. Okay? Alright, the intercept, it's a little bit weirder. Okay, the intercept is 34. Right? And the intercept is our interpretation, or is our prediction for y, when x is 0. Okay? Now, sometimes that number is negative. Okay? Here we have the intercept is 34. You could also have an intercept that's negative. You could have a slope that's negative. Okay? So positive or negative doesn't matter. But sometimes it doesn't make sense to have x equals 0. Okay? And sometimes the answer just doesn't make sense. Okay? So what this means is our prediction for a child who's 0 years old, so basically on the day of its birth, okay, our prediction for the height of that child is what? 34 inches. That's what we're saying here, okay? So we predict a child that is 0 years old to be 34 inches tall, okay? Now, that doesn't make sense, okay? Only because it doesn't match our intuitive sense, okay? Is it possible to have a child that's 0 years old? Yeah, I mean, the day it's born, it's 0 years old, okay? It's a couple hours born, or a couple hours or whatever. The moment it's born, it's 0 years old. That's fine, okay? But a 34-inch child, it would be a record-setting birth, okay? That's huge, okay? And that's only because our data, you know, whatever, you know, our model probably wasn't designed to predict children 0 years old. And it's not designed to predict people who are 100 years old, okay? Because according to our model, how tall is someone going to be if they are 100 years old? 234 inches, okay? 234 inches is like 20 feet tall, okay? It's 19 and a half feet. Doesn't make sense, okay? Doesn't make sense. Okay, But the interpretation of the slope and the intercept, slope is every time we increase x by 1, we predict the y to go up by the slope. The intercept is our prediction for y if x is 0. Okay, so let's try our sales in ice cream. Sales of ice cream in dollars equals, let me just think of a number here. Sorry, I gotta do okay, so let's say it's sorry, this is don't write this down. Don't write this down. Okay, I have no idea. Okay, so let's say you're running a little ice cream cart, okay? And this is the equation that we've come up with, okay? So temperature is in Fahrenheit, degrees Fahrenheit, and sales is in dollars. Okay, so according to this model, how much ice cream would you sell on a 90-degree day?
200.
So on a 90-degree day, we predict sales of, I would do minus 250 plus 5 times 90, okay? And I would get what? 200. Okay, so on a 90-degree day, I'm pushing my ice cream cart around. I might make $200 in sales. Who knows? Is that okay? All right. What about on a 80-degree day? Or let's say 85, yeah, let's say on an 80-degree day, we predict sales of what? Of 150, right? I do sales equals minus 250 plus 5 times 80, and I get 150. Okay, so far so good? Anybody confused? All right, what is my slope? The slope is 5. And what is the interpretation of the slope?
The temperature.
Huh?
Like the higher the temperature, the higher the sale.
Okay, yeah, so specifically, I would say,
Each time the temperature increases.
yeah, so
by
every time the temperature goes up by 1 degree, I expect my sales to change by what? I expect the sales to go up by $5, okay? That's the interpretation of the slope. each time for every additional degree in temperature. So for every additional degree in temperature, I expect sales to increase by $5. That's what that 5 means, okay? If it was negative, it means every time this goes up, I expect my sales to go down by this much, okay? So if I'm the sweater store, okay, maybe my slope would be negative $10. Every time the temperature goes up, I expect to sell $10 less in sweaters. Who knows, okay?
But why $5?
Huh?
Why $5? Because the slope is 5?
Yeah, the slope is 5. Okay, so my slope is 5. Every additional degree in temperature, I expect the sales to increase by 5. Okay. Alright, so let me just really quickly talk about residuals. Okay? So on a 90-degree day, I predicted sales of $200. Okay? What if I sold $240 worth of ice cream? So on a 90-degree day, I sold $240 of ice cream. Is that a good day, according to my model? Yes, according to my model, I outperformed my prediction by how much? $40, okay? I sold $40 more than what my model predicted, so this was a good day, okay? So the residual here, the residual is equal to actual minus predicted, okay? Or symbolically, residual, we use E for like error, but it's not really error, okay? The actual is just for Y, is equal to Y minus our prediction, which is Y hat. So here on this day, my E is 40 because the actual is 240, but I predicted 200 according to my model. Okay. Residuals can be positive or negative. If it was a 90-degree day and I sold $160, I would have negative $40 because my model said I should have sold $200 worth of ice cream, but I underperformed and I sold $40 less than what I predicted. Okay? And so with that, you'll have some exercises in your homework to go over. You know, if you have questions on your homework, please don't hesitate to post questions on the Facebook group, okay? It wasn't very active last week, so go ahead and post